So, hello, very good afternoon to all. Right, good. So, today what we are going to study, so this is our second part of this chapter, that is organic compound containing oxygen. So, in the previous class, we already discussed about the alcohol, phenols, and ether. So, in today's class, basically, we are going to discuss about the aldehyde, ketone, and carboxylic acid, right? So, these three things we are going to discuss today and try to do some questions as well on the basis of these three topics. Okay, so let's start with the today's session. I hope my voice is audible to all of you and my screen is also visible. Okay, so let's start with the today's session. Right. Okay. So what is aldehyde and ketone? So the first thing that come into our mind when starting with any chapter, that what do you mean by this thing, right? For example, aldehyde and ketone, because the name of the chapter is oxygen containing organic compound containing oxygen. So basically, we are going to study here the carbon oxygen double bond character, right? Carbon oxygen single bond we already discussed in case of alcohol, phenol, and ether. So here we are discussing about the carbon oxygen double bond. So what is this aldehyde and ketone? So basically aldehyde at least one hydrogen atom bonded to the carbonyl group, or the other group may either be hydrogen or an alkyl or allyl group. So it could be anything, right? There is no issue in it. So we can represent as this is. So this is the carbonyl compound group. So one must be hydrogen, right? So one must be hydrogen. It is necessary that at least one hydrogen atom is bonded to the carbonyl group. The other group may either be hydrogen. For I'm taking about the simple, if I'm taking CH3, so it will known as aldehyde. We commonly known as ethanol. So its IUPAC name is ethanol, and this is in a class of aldehyde. Similarly, this may also be write as 2H. This is also class of aldehyde. So this is known as the formaldehyde. Right. This is known as formaldehyde. So these are the necessary condition for the aldehyde, right? So anything which contain at least one hydrogen atom to the carbonyl group. In ketone, similarly, the carbonyl group is bonded to two alkyl group or two aryl group. Like we have a two alkyl group like 2CH3 and CH3. And we can also have a one CH3 group and one C6H5, that is aryl group, or both aryl groups. So either this is the very common name, and its common name is acetone. So we can know this thing acetone from our smaller class as well, right? What is acetone? Has a significant application of acetone. Now, so these are the classifications. If the two group bonded to ketone may be similar or different, resulting in the symmetrical or unsymmetrical ketone respectively, right? If the two similar group are present, then it is known as a symmetrical. If the two different group are present, then it is known as asymmetrical ketone, right? So this is how we can actually represent carbonyl group, an aldehyde group, and a ketone group, right? Now, you must be familiar with the vanillin and camphor, right? Their structure are given below. You can see that they contain an aldehyde and a keto functional group respectively. So in case of vanillin, which is used for the vanilla flavor in ice cream or in many way you need this vanilla flavor. So you use this. So they having a aldehyde structure, as we can see here. This is CHO, right? So this having an aldehyde structure, and camphor also having a keto structure, as we can see that is C double bond O. So they having a ketone structure. So this is in a structure of camphor and this is in a structure of vanillin. So these also contain aldehyde and ketonic functional group. Now, some common example of aldehyde and their names are given below. For example, HCHO we name as a methanol, or we say formaldehyde. Similarly, we can write ethanol, CH3CHO as a ethanol, or we also know commonly name is acetaldehyde, right? Similarly, CH3, CH2, CHO is known as a propanol, and their common name is propanoid aldehyde. Similarly, their common name is a benzene carbaldehyde, or we can known as benzaldehyde. So this is how will you name the aldehyde for the different aldehydes. Now, let's see some examples of ketones which are mentioned below, like acetone. This is the most common name, most common compound of ketone family, right? That is acetone. Another is a butane 2-on, also known as a ethyl methyl ketone. Cyclohexanone, we have a pentane 3-on, also known as a diethyl ketone. Pent 4-in 2-on, and next is acetophenone. So this one is also play an important role. Many questions have come. Acetophenone. So you must know the structure of acetophenone. That is benzene COCH3. So when the one alkyl group is aliphatic and one is aromatic, then it is basically known as a phenyl or we known as acetophenone. So always remember that acetophenone and one phenyl ethanone both are the same way, right? Similar benzophenone we have when the both the two groups are the aryl group, then we get the benzophenone, right? So this is how will you get benzophenone, acetophenone, and ketone. Now, how will you prepare aldehyde and ketone? So now this is going to be very important note because we already cover alkyl halide and alcohol, phenol, and ether, where we can saw how will you prepare aldehyde and ketone, right? So how will you prepare aldehyde and ketone? So one method we have like the oxidation of primary and the secondary alcohol. So from the last lesson, you know that the primary alcohol can be oxidized to aldehyde and secondary alcohol can be oxidized to ketone as well, right? So we know that the primary alcohol can be oxidized to aldehyde and the secondary alcohol can be oxidized to ketone. So how this takes place? Let me write example so that you can understand this thing. Like we have a formaldehyde, like we have ethanol, like CH3 CH2 and OH. So we have an alcohol. Now, when we treat with the oxidizing agent like KMNO4, right? KMNO4, or we use K2Cr2O7, we can use either of them, K2Cr2O7, right? So we'll get CH3 and this is nothing but CHO, right? So here oxidation takes place from alcohol to we get the aldehyde. So the oxidation takes place, right? Similarly, if you take the secondary alcohol like CH3 and this is CH, this is OH and this is CH3. So this is nothing but propane to all. So this is a secondary alcohol and oxidation of this secondary alcohol as well, like when they treat with a K2Cr2 and O7. So when we treat with this K2Cr2O7, it will convert it into CH3CO and CH3. That is acetone. Right. So we'll also prepare ketone from this method. So that's what I write about that when you treat primary alcohol with the oxidizing agent like KMNO4K2Cr2O7, you'll get aldehyde. Similarly, when you treat secondary alcohol with the oxidizing agent, you get ketone. So this is how will you get this thing, right? So this is the way to prepare aldehyde and ketone by the oxidation of alcohol. We know that by the reduction of aldehyde and ketone with the reducing agent and the Grignard agent, we are able to produce alcohol back, right? We already discussed this thing. So just by the oxidation of alcohol and the secondary alcohol, we get this. Now, one question comes into your mind that what about the tertiary alcohol? What is happening in case of tertiary alcohol? So if you have a tertiary alcohol like this, now, when we treat with again K2Cr2O7, K2Cr2O7, then there will be no reaction. So why no reaction takes place? No oxidation takes place. Why this is takes place? Because as we can see now, in this carbon, they do not have any hydrogen, right? So they do not have any hydrogen, so their oxidation can't take place. What is oxidation? Oxidation either addition of oxygen or the removal of hydrogen. So in both these cases, removal of hydrogen will take place. But in this carbon does not contain any hydrogen, so the removal of this hydrogen won't take place. And due to this reason, tertiary alcohol do not undergo oxidation, right? So tertiary alcohol do not undergo oxidation, where the primary undergo oxidation to give aldehyde and secondary undergo oxidation to give acetone, right? So I hope this is clear to you. Good. Now, the next method for the preparation is that is hydration of alkynes. So this is another important method that is by the hydration of alkyne we can also prepare aldehyde and ketone. So how? Let's see. Hydration of alkynes can give an aldehyde or ketone. Basically, Marconic hydration yield a ketone, where anti-Marconic hydration give aldehyde. So hydration of alkyne. So first of all, in alkyne we need to treat alkyne with the water, right? So it gives an aldehyde and ketone. So when we will get aldehyde, we will get ketone. So basically, Marconic hydration give us ketone. So when you add water according to the Marconic's rule to the alkyne, then you will get the ketones, where the anti-Marconic hydration give the aldehyde. So let's see how this thing takes place. So as we can say that we have an alkyne here, right? Triple bond, RC, triple bond. Now they are treated with Hg2 plus H plus in presence of water. So this water, we know that we can write water as OH negative, NH positive. So because since this is a symmetrical alkane, right? R C triple bond C H. So how will you know this negative part goes to those carbon atoms which contain the lesser number of hydrogen. So here both are same. So this OH negative comes to this carbon, this R is left with this, and this H and this H. So this is known as, now they are further react and they will give the ketone form, right? So whenever the here we do according to the anti-Marconi's rule or Marconi's rule. So according to the Marconi's rule. So according to the Marconi's rule, if you do this, then you will get this, right? So this is what you have. Now similarly, if you treat alkyne with this with BS3, and they will get this compound only, that is aldehyde, right? So always remember that anti-Marconi's hydration give always aldehyde, where the Marconi's addition gives ketone only. So this is how will you prepare. Now the next method, this is also very important, that is the Friedel-Crafts acylation. So basically the aromatic ketones can be prepared by Friedel-Crafts acylation, that is alkynolation reaction. So let's see some example of this reaction. So here we have OCH3, right? Like we can say that we have an anisole. So we have a CH3O, and when they are treated with the CH3COO, COCH3 or AlCl3CH2, and HCl and H2O, then we'll get this. Similarly, acylation reaction using ethanoyl chloride was discussed in lesson that we already discussed in the previous lesson under the electrophilic substitution reaction, right? Now, let's see some structure and the physical properties of aldehyde and ketone. So, what structure they actually possess? So, basically, in both aldehyde and ketone, the carbonyl carbon and oxygen atom are sp2 hydride. How? Let's see. We know that. This is the structure of aldehyde or we say ketone. Now, if I'm talking about the hybridization of carbon, then hybridization of carbon is nothing but is equal to number of sigma bond plus lone pair of electron. So here we can say that number of sigma bond is nothing but 1, 2, and 3. So number of sigma bond is 3 and lone pair is 0. So 3 means what? This will form sp2 hybridization. So this will form sp2 hybridization. Similarly, if I want to calculate the hybridization of O, then how will you find out? The hybridization of O is nothing, but it will make only one sigma bond. So it will form one sigma bond. And how many lone pair they have? So they have no, yeah. So they have two lone pairs. So this is three. Sorry, two. So this comes out to be three. So three means again sp2. So we can say that in a aldehyde or ketone, the carbonyl carbon and the oxygen atom are sp2 hybridized. Therefore, the group attached to the carbon atom and oxygen are present in a plane, right? Because we know that the sp2 hybridization having say planar shape. So this is shown in the figure. This is the structure. So this is pi bond is formed between the p orbitals, and this is the two lone pair of electrons of the oxygen atom, right? This is the lone pair. This is the carbon having empty. They have only sp2 orbital now, sp2 hybridization. So it means this and this have a vacant orbital, right? So this vacant orbital will make bond with this vacant orbital, and these two lone pair of electron remain the same, right? So pi bond is formed between the p orbital. Now, carbon atom gets a partial positive charge. This polar nature of the carbonyl group makes the oxygen atom nucleophile and basic, while the carbon atom become electrophile, right? So this polar nature of the carbonyl group, why this polar nature comes into the picture, beta? Basically, the polar nature of the carbonyl group. What do you mean by this thing? That is the polar nature of the carbonyl group. Basically, due to presence of more electronegative oxygen, as the oxygen is more electronegative, it requires partial negative charge, and this require partial positive charge. So the polar nature of the carbonyl group make the oxygen atom nucleophile because they want to shift the electron towards itself and become electron rich. So they behave like a nucleophile and the basic. While the carbon atom become electrophile because they feel the deficiency of electron. Now, the physical properties and the chemical reaction of aldehyde and ketone are direct consequence of this polarization, right? So the physical properties and the chemical reactions of aldehyde and ketone are directly depend upon this polarization. Now, let's see some reaction of aldehyde and ketone. So what reaction they generally show us, that is the reaction of aldehyde and ketone. So if you examine the structure of the molecule of the carbonyl compound, you will find that there are three center of reactivity and is shown below. So what are the three center of reactivity? That is C double bond O, and they have either two group. So if I'm talking about the aldehyde group, that is C O and is having C H and R. So this prone to attack by the electrophile. So this negative part. So this prone to attack by the electrophile, susceptible to attack by the nucleophile. So this will show that prone to attack by the electrophile because electrophile having deficiency of electron and they want electron. So the oxygen having negative charge, so they can donate electron. However, carbon also acquire positive charge, so they have a susceptible to attack by the nucleophile. Now, this C and R. So this H have an acidic hydrogen because they are alpha carbon. So alpha hydrogen are more acidic in nature as compared to this, right? So this is all about. So you'll find the three center of reactivity. So three center of reactivity means we have a electrophile, nucleophile, and presence of as well acidic hydrogen as well. Now, since the oxygen atom is nucleophile in nature, it is attacked by the electrophile, whereas the carbonyl carbon is the electrophile nature and hence it is attacked by the nucleophile. The third site of the reactivity is hydrogen atom present at the alpha carbon atom. So this is the third site of reactivity is the hydrogen atom which is present at the alpha carbon. Right. So it is acidic in nature and give a typical reaction which will be studied in this section that we are going to study. So it is acidic in nature. So why they are acidic in nature? Due to presence of alpha hydrogen. So this point you can also remember. Now, it is also important to know here that aldehyde are more reactive than ketones. So why this is taking place? Why aldehyde are more reactive than ketones? So this is because of the following two reasons. The first one, aldehyde have only one alkyl group, whereas ketone having two. Since the alkyl group are electron donating in nature, let me first write the structure here so that you can understand this thing in easy way. So this is aldehyde and this is nothing but ketone. So, since alkyl group are electron donating in nature, that R group, the carbonyl carbon in ketone is bonded to the two alkyl group is less positive, right? Means it is a less electrophile because these two donor group are present, which makes it less electrophile because they continuously give electron to the carbon. So the carbon will feel less deficiency of electron, or we say they feel less electrophile as compared to the aldehyde carbonyl carbon as compared to the aldehydic carbonyl carbon, right? Hence it is a less susceptible to attack by the nucleophile. इसीलिए hence it is the due to reason they are less susceptible to attack by the nucleophile. Now, let me explain with this example because we know that here two donor group are present. So these two donor group can give the electron towards the C. Thus the C become less electrophile. So if they are become less electrophile as compared to the aldehyde carbonyl carbon, right? So aldehyde carbonyl carbon means if they have a less. So this is alpha H, right? That is COCHO. So this is alpha H. So if due to 2R group, if the 2R group is present at this point, understand this thing. If the 2R group is present at that time, then it will just make us. Hence, it is the less susceptible to attack by the nucleophile. The two alkyl group in ketone also make the carbonyl carbon more crowded as compared to the carbonyl carbon in the aldehyde. This factor also makes the aldehyde carbonyl carbon more susceptible for attack by the nucleophile as compared to carbonyl carbon of the ketone. With this background in mind, let us now study the reaction of the aldehyde and ketone. So just remember this point because this point is very, very important. That is out of aldehyde and ketone, aldehyde is more reactive than ketone. And why this is happening? Because it is happening because aldehyde we have only one donor group, but in ketone we have a two donor group, which makes us less reactive than the aldehyde. Right now, let's see some reaction so that you can understand this thing in a easy way. So the first reaction that aldehyde undergo is that nucleophilic addition reaction. So always remember that aldehyde show nucleophilic addition reaction, right? So nucleophilic addition reaction. So the general reaction of the addition of nucleophile on the carbonyl group can be represented as the following. How? So this is the aldehyde, carbon having partial positive charge and oxygen having partial negative charge. And we know that nucleophilic having negative charge and delta H having positive charge. So what the reaction takes place? We know that this nucleophile can attack to this, and this behave like an electrophile. So the nucleophile attack here, this behave as a nucleophile. So here electrophile will attack. So what the reaction will take place? The reaction become RHC, and this is nucleophile, and we have also like a OH, right? So this is the nucleophilic addition reaction. Now, what is the mechanism of this nucleophilic addition reaction? So basically, under the basic condition, the nucleophile attack at the carbonyl group yield a tetrahedral intermediate, right? So as we can see that there is a tetrahedral intermediate. So under the basic condition, the nucleophile attack at the carbonyl group yield a tetrahedral intermediate. Subsequent to this, the protonation from the solvent as H2 or alcohol takes place. This is shown below. For example, as soon as the nucleophile attack to this carbon, right? So this is the formation of a tetrahedral intermediate. Now, what is happening here? That is this is become O negative. So H2 here H2 will be removed. So this will become and tetrahedral product, that is this one, and this will become OH, right? This attack of H takes place from the water. So it will become HOH. Now this will be OH negative. However, in the acidic condition, the first step of protonation of the carbonyl oxygen takes place. So how this the protonation takes place? That is, the HA will accept this. So this will accept this and will form H plus OH negative. The nucleophilic then attack in the second step to the carbonyl carbon, and the addition process is completed. Right. So some specific reaction of this category, let's discuss. For example, formation of cyanohydride. So let's see how the formation of cyanohydride takes place. So basically, carbonyl compound react with hydrogen cyanide to give cyanohydride. For example, we have a propanone. So we can remember this reaction like we have a CO and we have a two different group like CH3 and CH3. Now, when we treat with SCN, we know that H having a positive charge, CN having negative charge. So when you treat this, this also behave like a positive and negative. So this negative part come to this atom, this positive part comes to this atom. So what the formation will be takes place? That is nothing but CH3. This is again CH3, and this is nothing but OH, and this is nothing but CN. Right. So this is how the procedure takes place. So note that one more carbon atom is present in the cyanohydride as compared to the starting carbonyl compound, right? So one more addition of carbon will takes place. So cyanohydride are useful in the synthesis of carboxylic acid, about which we are going to study in the next chapter, that is on carboxylic acid. Today we are going to cover this thing as well, right? So the cyanohydride are useful in the synthesis of carboxylic acid. Now, the next is that is the formation of hemiacetal. So what is this? This is also very, very important. Formation of hemiacetal. So aldehyde and ketone react with alcohol to give hemiacetal. Hemi in Greek means half, right? So hemiacetal means half acetal. So hemiacetal have an OH and OR group attached to the same carbon atom in their molecule. So hemiacetal means what is taking place beta, that is having OH and OR group attached to the same carbon. So when excess of alcohol is used, a second molecule of the alcohol react to give a acetal. Right here we can see through example, because we have ethanol and methanol. So this will give a hemiacetal. Right. Then again, it will convert with another CH3COS, it will give the acetal. Similarly, it will give hemiacetal and later it will give an acetal. So note that the acetal has a two OR group attached to the same carbon. Right. So I hope you remember this thing. Now, acetal are stable in the basic solution and are therefore used as a protecting group for aldehyde and ketone, because these acetal are stable in the basic solution and are therefore used as a protecting group of aldehyde and ketone. Now, acetal can be converted back to the carbonyl compound by treating them with the dilute acid because of the reversible nature of the above reaction, right? So this is what is all about, right? Now let's see the next chemical reaction. So before going to the next chemical reaction, you must remember this thing. You must revise this thing so that you can know this thing, which type of chemical property generally shown by the aldehyde and ketone, right? So let's move to the next one. Right. So let's see. Formation of alcohol, or we say Grignard region. So RMGX, as also known as the Grignard region, they react with an aldehyde and ketone to give alcohol as the shown in the figure. Because we know that now, whenever we treat is the method of preparation of alcohol as well, when we treat carbonyl compound with the Grignard reducing agent and Grignard agent, we get the alcohol, right? For example, if we treat formaldehyde, if you treat formaldehyde with the with the Grignard reagent, we'll get the first degree alcohol. Similarly, if you treat aldehyde with the Grignard reagent, we'll get the second degree of alcohol. And similarly, if you treat Grignard reagent with the ketone, then we will get the tertiary alcohol. So this we already discussed. Right. Now, let's see the next one. That is this nucleophilic addition reaction we already covered. So, in the nucleophilic addition reaction, we cover alcohol, Grignard reagent, hemiacetal, and the cyanohydride. So, this three reaction that will cover in the nucleophilic addition reaction. Now, this is the addition, elimination, or we say condensation, right? So, this is the addition. So, which type of addition this is? Elimination or condensation. So basically, the reaction with ammonia and its derivative, aldehyde and ketone, react with ammonia and the primary amine to give imines, right? To give imine, to give imines. So, which are compound having a carbon nitrogen double bond. So always remember this, wherever you get the bond like this, carbon nitrogen double bond, then this bond is known as imine. Always remember, this is known as imines. Right. So the reaction with the ammonia and derivative, aldehyde and ketone react with ammonia. Aldehyde and ketone react with ammonia and the primary amine to give imine, which are compounds having the carbon nitrogen double bond. Right. So we can see that here when you treat ketone with the ammonia, we'll get in the acidic medium, we'll get NH imine. That is called imine. Similarly, if you treat primary amine, just remember this formula that how we will remove this. Then this H2 will be removed and this will form R N double bond C. or we say CNREME, or we say skip base, so also known as skip base. Okay. So this is how we'll get this thing. Now, it's appear that during the above reaction, a molecule of water is lost from the primary amine and the carbonyl compound. So it is appears that during the above reaction, a molecule of water is lost from the primary amine and the carbonyl compound. So the reaction with the other derivative of ammonia are given as hydroxylamine. So for such reaction, just remember one useful thing, right? Just remember the pattern here. Like we have a aldehyde or ketone, it may be anything. Remember this thing. We have a H2N, and here we'll use different group. Right. So if you use this group OH, then we'll get oxide. Similar, if you use this group NH2, then we'll get a hydrogen, right? So on the similar basis, here in all reaction, elimination of H2 will be takes place. So this is an example of the elimination reaction, right? So hydroxylamine, and the hydrazone, this will be formed. Similarly, phenyl hydrazine, because here we're using, H2 is removed, we're using NNH and this whole benzene group. So this is known as phenyl hydrazine. So we'll get the phenyl hydrazone. Similarly, we have a 2,4-dinitrophenyl hydrazine, also known as the 2,4-DNP, right? So 2,4-DNP. So we'll get this thing also, right? So I hope this is clear to you. Right. So this is how will you get this compound. Basically, the compound formed above are relatively insoluble solid, have characteristics melting point. So these compounds can be prepared from the unknown aldehyde or ketone, and their melting point can be determined. So these melting point are matched with the derivative of already known aldehyde and ketone listed in the standard table, and the carbonyl compound is thus identified. Right. So this is how you can identify. Now we are going to study the different type of reaction, C type. We already studied the substitution reaction. Sorry, nucleophilic addition reaction. We already studied, and later we are studying about the condensation, right? That is the nucleophilic condensation or elimination reaction. Now, the C type of reaction, that is called a deoxygenation reaction. So, deoxygenation reaction are the reaction involving the removal of oxygen. Like aldehyde and ketone can be reduced to the corresponding alkanes by the following two reactions, right? So, this is the method in which you reduce aldehyde and ketone into alkane. So as the name suggests, deoxygenated reaction. So deoxygenated means that is aldehyde and ketone can be reduced to the corresponding alkanes by the following two reactions. The first one is Wolff-Kishner reduction. First reduction is Wolff-Kishner reduction. So when an aldehyde or ketone is heated in a basic solution of a hydrogen in a high boiling alcohol, then the carbonyl group gets converted to a methylene CH2 group. Right, so we'll get this compound like a C double bond O CH3 NH2 NH2 OH H2O. So we'll get ethyl benzene. So always remember this. In Wolff crystal reduction, we always use the reagent reducing agent like NH2 NH2 OH negative NH2. Right, so NH2 NH2 OH negative heated NH2. So we'll get the ethyl benzene. So this is the Wolff crystal reduction. And the next one is the Clemson's reduction. So basically, it is carried out in the acidic medium using a amalgamated zinc. So zinc amalgam is used in this and hydrochloric acid. So when you treat heptanol with the zinc amalgam HClH2, you will get heptane. That is CH3 and CH2 5 CH3. You will get the heptane. So this is all about the Clemson reduction, right? So this is what. Now, the fourth type of reaction we also have, like this is called the oxidation of aldehyde. So, unlike ketones, aldehyde can be easily oxidized to the carboxylic acid. So, unlike ketone and aldehyde can be easily oxidized to the carboxylic acid using a variety of oxidizing agents. These reasons can be chromic acid, chromium trioxide, permanganate, or silver oxide. So, you already read about the oxidation with the some of this region, like when the silver ion selectively oxidize CHO group only. This is also known as a tolerance region test. So this forms the basis of tolerance test. So it involves the addition of the mixture of aqueous silver nitrate and aqueous ammonia, which is known as a tolerance region to the carbonyl compound. Now, tolerance region contain AgNH3 twice plus complex ion. If an aldehyde is present, it gets oxidized to the carboxylic acid, whereas the Ag plus ion reduced to form silver metal, which get deposited on the wall of the test tube, and this gives a mirror-like shining appearance, right? So this is what thing is. Now here we have a aldehyde, like aldehyde. So AgNH3 twice having an aldehyde, they will convert it into carboxylic acid with the silver mirror test. Now, aldehyde are also oxides by the Fehling solution, which contain copper plus two copperic ions complexes with a tartrate ion as the oxidant. These copper plus ion are reduced by the aldehyde in alkaline medium to give a brick red precipitate of the copper sulfide. So Torrance reagent and this the Fehling solution all react with the aldehyde. Right. So now this is going to be very important reaction. So remember this. Many time in your examination questions were coming related to this topic only. That is the alpha hydrogen in aldehyde and ketone is a quite acidic and they can be easily abstracted by a strong base. So basically the alpha hydrogen in aldehyde and ketone is quite acidic and no this can be easily abstracted by the strong base. For example, this we have a keto form like we have a OHCHO. So this is the alpha hydrogen. So basically this is a group we have like OH, and R, and this is an C, and this is H. So this is a keto form, right? This is a keto form. So this is called as a alpha hydrogen. So this alpha hydrogen is easily, we can also write this structure. So this alpha hydrogen can easily extract by the strong bases. So the resulting anion can be stabilized by the resonance as shown in the above. This is called an enolate ion. On protonation, it gives an enol, right? Thus, keto form and enol form are in equilibrium. Thus, it is also known as a keto enol tautomerism. So it is also known as a ketone tautomerism. Now let's see the first one, that is a halogenation. So ketone having alpha hydrogen atom react directly with halogen and alpha ketone are obtained as the product. This reaction is promoted by the side acid and base. For example, we have a CHCHO plus H2H plus and OH negative will get alpha halo product. Similarly, let's see if we have X2 which is equal to either Cl2, Br2 or I2, so we have a propanol that is at CH2COCH3. When they are treated with Br2CH3COH, it will give a bromopropanol. Similarly, if we have like this, then we'll give the trihaloketone, right? Or a trihalo group is a good living group, and the trihaloketone react with the OH, which finally give the carboxylic acid. Now, this reaction is called the haloform reaction after the name of the product. Now, if the iodine is used as the halogen, then we get the iodoform, right? Now, iodoform is bright yellow solid having a characteristic melting point. This reaction that form the basis of the iodoform test. This methyl ketone give a positive iodoform test. Now, this one is going to be very important. That is the aldol condensation. So what is this aldol condensation? So basically, aldehyde having alpha hydrogen atom on reaction with the dilute NaOH give aldol. So always remember, first condition is it must be an aldehyde and having alpha hydrogen atom on reaction with the dilute NaOH, it give aldol. This reaction is illustrated below by using a ethanol as the example. For example, you have a ethanol, where another have a ethanol. So, they will react with the KOH or NaOH dilute in H2 at 778 kilo 78 Kelvin. So it will give us 3-hydroxybutanol, or we known as an aldol product. So note that product contain both the aldehyde and the alcoholic functional group, and therefore it is called aldol. Aldol addition product on heating undergo dehydration to give alpha beta unsaturated aldehyde, which is a condensation product. Now, this is aldol and this is transbutyl. So, this completely sequence of reaction is called aldol condensation. So, aldol condensation is also possible with the ketone. Can you think a little more complex situation? What will be the product of aldol condensation when the two different aldehyde having alpha hydrogen atom are used? So, we get the four different products, right? Now, in this case, the reaction is called a cross-aldol condensation. This is left in its size for you, right? So, this is how we can actually assume that when the two different aldehyde both having alpha hydrogen having treated, then how to get the product. Thus, the product obtained either will be four product. I already told you that is AA, BB, AB, and B. Now, let's see some Cannizzaro reaction. That what is Cannizzaro reaction? So basically, aromatic or aliphatic aldehyde which do not have alpha hydrogen and reaction with the concentrated NaOH or KOH give one molecule of and alcohol and sodium salt of the carboxylic acid, right? So basically the aromatic or aliphatic aldehydes do not have alpha hydrogen. So this is the necessary condition for the aldol condensation, that is must possess alpha hydrogen. So if they do not have any alpha hydrogen, then we will undergo Cannizzaro reaction. So this reaction is known as the Cannizzaro reaction. So in this reaction, one molecule of an aldehyde is oxidized to carboxylic acid, sodium or potassium salt, and another molecule of the aldehyde is reduced to the alcohol molecule. So in this both oxidation and alcohol takes place, so we can name it the disproportional reaction. So here we can see the example. For example, we have a methanol, right? This is nothing but methanol, not methanol. Methanol we have and treated with concentrated H2SO4 will give the methanol and potassium torbate. Similarly, if we have a benzaldehyde HO in the presence of concentrated NaOH, it will produce this into a benzyl alcohol, right? Produce into benzyl alcohol. So in all these cases, we observe that both alcohol and oxidation both will be takes place. Now, thus we can say that the disproportional has occurred and simultaneously oxidation reduction has to take place to give one molecule of a carboxylic acid and R molecule of an alcohol from the two molecules of the starting aldehyde. So this reaction is limited. This reaction is limited to those aldehyde only which have a no hydrogen, right? Or we given only with possible with those aldehyde which having alpha, which do not having alpha hydrogen, and the aldol condensation is possible with only those having alpha hydrogen. Can zero is do not having alpha hydrogen, right? So this is all about. So I hope this is clear to you. Now after 2 minutes, we are going to study carboxylic acid, right? Take some water, and after 2 minutes, we are going to start carboxylic acid as well, right? Right. So let's see some next thing, that is carboxylic acid. Okay. So we already discussed about the aldehyde and ketone. So in next that what we are going to study, that is carboxylic acid, right? So let's see what are the important things that we are going to do in the carboxylic acid. So basically, wait, yeah. So how will you prepare carboxylic acid? So before let's see some structure of carboxylic acid, so you get the overall idea that how this look like, right? So basically carboxylic acid, just like a aldehyde, we have a formaldehyde. So just like a formaldehyde, we have a here formic acid, right? Formic acid we have, ethanoic acid we have, and the benzoic acid we have, also known as the phenyl methanoic acid, right? So carboxylic acid containing two carboxyl group are called dicarboxylic acid. So if you have a two COH group, then they are known as a dicarboxylic acid. Now, how will you prepare carboxylic acid? So first by the oxidation of alkenes. So alkenes on oxidation with the hot alkaline KMnO4, this will give us the carboxylic acid. For example, when you treat RCH alkene with the KMnO4 and OH, you will get the carboxylic acid. Similarly, we'll get the oxidation of alcohol and aldehyde as well. So we know that whenever we'll take aldehyde, that is like CH3 and CH2 and OH, we have alcohol. Now, in the oxidation in the presence of KMnO4, so this will give us CH3 CHO. But this reaction won't stop here. They further react with the nascent oxygen provided by the KMnO4. So give CH3 COH, right? So if you want to stop at this level only, then you have to add an agent like PCC and PDC, right? So you have to add an reagent like this PCC and PDC. This is how will this alcohol will convert it into aldehyde. If you want to add this agent like PCC and PDC, then this aldehyde will be further converted into carboxylic acid. So we already read about this in a previous section of this lesson that alcohol and aldehyde can be oxidized to carboxylic acid using a variety of oxidizing agent. Right now, let's see oxidation of alkyl benzene. For example, if I'm talking about the primary and the secondary alkyl group attached to the benzene ring can be oxidized using a alkaline KMnO4 to the carboxylic group, right? So the primary and secondary alkyl group. So this reaction is very important. Whether there will be one CH3 group, we have a methyl benzene, either we have a methyl benzene, or either way we have a cumene. Doesn't matter, no matter what group we have, we if we have a group like this also, like ch3 ch3 and h. So in this case also, if you treat with the KMnO4, then what you'll get only benzoic acid, right? So this thing is very very important. Whether you'll have a one CH3 group of the benzene, or we have a more than CH3 group, or we have a many complex rival structure, doesn't matter, you in the product you always get the benzoic acid, right? So the primary and the secondary alkyl group attached to the benzene ring can be oxidized using KMnO4 to the carboxylic acid. So acidified sodium dicarbonate can also be used for the reduction, like Na2Cl2O7 H2SO4. So this can also convert this. This is known as the parachlorobenzoic acid, right? So acidified sodium dichromate solution can also be used. Now, the next method is that is a carbonation of the Grignard reagent, that we should prepare this from the Grignard reagent as well. So how will you prepare from the Grignard reagent? So basically from the Grignard reagent like RMGX, this react with the carbon dioxide to give magnesium carboxylate, which on acidification gives the carboxylic acid, right? So when you treat with the Grignard reagent, when you treat Grignard reagent with the CO2, then what you'll get will get like RCOMGX, right? And again, when the acidic hydrolysis, you'll get RCOH, right? So this is how will you get this thing. So basically the Grignard reagent, that is the RMGX, react with the carbon dioxide to give magnesium carboxylate, which on acidification give the carboxylic acid like this, right? Similarly, if we have like a chloroethane, like a CH3, CH2 and Cl, when this CH3, CH2, Cl is treated with magnesium in the presence of ethyl oxide, then we'll get the Grignard region. And again, we'll get the propanoic acid as well. Here also we have a Grignard region, RMGX, MGBR. When they're treated with the CO2 and H2, we'll get the benzoic acid. So what you need to remember from here, when you treat Grignard region with the CO2 followed by the acidic hydrolysis, right? Then you'll get the carboxylic acid, right? Let us assume if you have CH3, this is CH3, and this is Mg, and this is Br. Right, this is Grignard region. Now, when you treat with CO2, what you will get? So when you treat with CO2, you will get nothing but CH3 This is nothing but C double bond O. So we can write as this, yeah. And this is Mg and Br, right? So this will become CH3 and CH3, this will become CO and this will become Mg and Br. Now further hydrolysis, on hydrolysis, MgBrOH will be removed out and we'll get CH3, C double bond O, this is O and H. And what is left? Left is nothing but MgBr and OH. Right. So this is how will you get one reaction with the CO2. Similarly, when you treat chloroethane like CH3, CH2, Cl with magnesium E2O, then we'll also get this the same thing, right? So note that there is an increase of one carbon atom in the carboxylic acid as compared to the starting alkyl halide, right? So there is an increase in the one carbon atom because here we can say that number of carbon atom is only six, but here we can observe that there is a seven carbon atom, right? So there is an increase in the one carbon atom in a carboxylic acid as compared to the starting alkyl halide. Okay. Now, hydrolysis of nitriles and cyanohydride. So basically, alkyl halides can be converted to nitriles, which on hydrolysis give carboxylic acid having one or more carbon atom than the starting alkyl halide, right? So the alkyl halide can be converted to nitriles, which on hydrolysis give carboxylic acid having one or more carbon atom than the starting alkyl halide. Like let's see the example. If we have alkyl halide like RCH2X and they react with the cyanide, it will form nitrile like RCH2C. On further acidic hydrolysis, it will form into ethene. And now when we treat with the subbase, it will convert it into RCH2CO, NH3. Now again with hydrolysis, you will get the carboxylic acid, right? So alkyl halide can be converted to nitriles, which on hydrolysis give carboxylic acid. So this is the way. Just remember the one or more carbon atom and then the starting alkyl halide. Here also we have a one and two dibromoethane. Now when treated with the NaCl, it will converted into NCNC. Now again hydrolysis will get the 2COH group. So this is called a butane dioic acid. So this will play a very important role. So learn this thing. For example, if you have CH3, CH2, and this will have CO. Now, when you treat with this with the KCN, what is happening? This KCl will be removed, right? This KCl will be removed, and what you will get? You will get CH3, CH2, and CN. Right? This is what you will get, CN, nitrile. Now, the hydrolysis of nitrile. So, hydrolysis of nitrile will get this thing like R, or we say CH3 CH2 COH. So this is how will you get this, right? Similarly, cyanohydrine obtained from the aldehyde also give 2-hydroxy carboxylic acid on the hydrolysis. So this is all we get this thing. Right. So let's see the some structure and the physical properties. So let's see the structure and physical properties of an aldehyde. So similar to aldehyde and ketone, the carboxylic carbon atom is sp2 hybridized. So in this case also the carboxylic carbon, because this carbon is belong to carbonyl carbon as well. So this is sp2 hybridized. Thus the three atom attached to this carbon which is lie in the same plane with an approximate bond angle of 120 degree between them, as we know. Now, carboxylic acid form hydrogen bond because of the presence of polar carbonyl and hydroxyl group. So this will form a hydrogen bond, right? Most carboxylic acid exist in dimeric form in which two carboxylic acid molecules are held together by the two hydrogen bond, and this as shown in the figure. So here we have a hydrogen bond and this is a dimer of carboxylic acid like RCOO, RCOO. So this having a hydrogen bond. So due to this cyclic structure and strong hydrogen bonding, they possess a higher boiling point as compared to alcohol even, right? So in the organic chapter, if I'm comparing about the alcohol, alkyl halide, or we say halogen, compound containing halogen, alcohol, ether, carboxylic acid shows maximum boiling point due to the presence of carbonyl group as well as the hydroxy group. This will make a cyclic structure as we see in the slide. And due to this cyclic structure, this bond become very, very strong and difficult to break. Thus, we can say that they show high boiling point, right? So you must remember this thing. Now, let's see some features of the carboxylic acid. That is the acidity of the carboxylic acid, right? So what is the acidity of carboxylic acid means? Basically, the carboxylic acid are acidic in nature. Okay, so they dissociate in water according to the following equilibrium to give a proton and carboxylate ion. So basically, carboxylic acid are acidic in nature and they dissociate in water according to the following equilibrium to give a proton and a carboxylate ion. Like carboxylic acid dissociate RCOOH, they react with H2O, they dissociate in the form of RCO negative plus H2O plus, right? Better we can write as this will be H2O plus, no, this will be H3O plus, right? So this will gives us a carboxylate ion. So basically, the carboxylic acid are acidic in nature. They dissociate in water according to the following equilibrium to give a proton and a carboxylate ion like this, right? This is carboxylic acid, this is water, and this will form carboxylate ion. Remember that lower the pKa indicate greater acidity. We already know this thing from the alcohol chapter as well. If someone having a higher Ka value, it means they have a good acidic in nature and lower pKa value. pKa value is inversely proportional to the Ka value, right? So if you compare this pK value with those of alcohol, you will note that the carboxylic acid are much more acidic than alcohol. So this can be also explained on the basis of anion formed as a result of ionization. So basically, the carboxylate ion obtained by the dissociation of carboxylic acid can be represented as a resonance hybrid of the following two structures. As we can see here, so this is the resonance structure of the carboxylate ion. So they show two resonance structures, carboxylate ion, right? So basically, the carboxylate ion obtained by the dissociation of carboxylic acid can be represented as a resonance hybrid. Now, you can also see below that as the number of halogen group increase, or we say as the number of electron withdrawing group increase in the carboxylic acid, acidic character also increase. So remember one thing, for acidity, if electron withdrawing group increase, then acidity also increase. Now, if the electron donating group increase, then acidic characters start decreasing. Remember this thing. So you can see that below the number of halogen at a group increase in the carboxylic acid. So its acidity increase. Why? So this is because they make the release of H plus ion more and more easy. Why? Because one group is already electron withdrawing group. So due to this, they make the no release of H plus ion more and more easy. Like we have a ethanoic acid, we have a chloroethanoic acid, we have a dichloroethanoic acid, and we have a trichloroethanoic acid. So their acidic value, we know that lesser the value of pKa because pKa value is inversely proportional to Ka, and Ka value is directly proportional to the acidic nature, right? So we can observe this. So we can say that as the more and more number of electron withdrawing group increase, that is chlorine like atom increase, as in case of a trichloroethanoic acid, we get the pK value is 0.70. It is the lowest pK value. So lowest pK value means what? They having highest Ka value, right? They having highest Ka value. And due to this, acidity start increasing. So this is because they make the release of H plus ion more and more, right? So I hope this is clear to you that what is the reason behind this and how you can saw that the carboxylic acid having more acidic in nature as compared to alcohol phenol and all this thing, and how electron donating and withdrawing group affect the acidic nature, right? So this is how they affect. As the number of electron withdrawing group you start increasing, as the number of electron withdrawing group start increasing, their behavior also changes, right? So this is how you can identify. Now let's see the next one. Since the inductive effect decreased with the increase in the distance of the group in the carbon chain, so the 2-chlorobutanoic acid pK value 2.86 is more acidic than the 3-chlorobutanoic acid because we know that here since the inductive effect decreases with the increase in the distance, this will show more inductive effect as compared to 3 and as compared to the 4, right? This is a 4-chlorobutanoic acid. 1, 2, 3, 4. Yeah, right. So this here correction is needed. So chlorine is at this atom. 1, 2, 1, 2. Right. This is. So this is 2-chlorobutanoic acid having more acidic in nature as compared to 3-chlorobutanoic acid and the 4-chlorobutanoic acid. So acidic value increasing. Right. So this is how acidic value start increasing. Right. Or decrease the we can say that decrease in the eye effect. So we can say that as the distance increases, eye effect will start decreasing. So this is how we get this. Since the inductive effect decrease with the increase in the distance of the group in the carbon chain, so 2-chlorobutanoic acid having pK value 2.86 is more acidic than the 3-chlorobutanoic acid having pK value 4.05, which is in turn more acidic than the 4-chlorobutanoic acid, right? Now, let's see reaction of the carboxylic acid, right? So carboxylic acid are completely deprotonated by the strong bases such as the metal hydroxide to give the salt, right? So the carboxylic acid are completely deprotonated. For example, here we can say that this is an ethanoic acid like CH3COOH plus NaOH. This will easily give us sodium ethanoate. So it will be interesting to know that the soaps are the sodium salt of long chains of carboxylic acid which are called the fatty acid. So this is known as saric acid, CH3, CH2, 16, COH, NaOH. They will become sodium cerate or we can soap. Soap having the chemical formula of sodium saturate. Right. Now, it will be interesting to know that the soaps are the sodium salts of long chain carboxylic acid, which are of called fatty acid. So we can observe this. This carboxylic acid are also deprotonated by the weak base, such as the sodium bicarbonate. In this reaction, they form sodium salt for the acid, carbon dioxide, and water. So this is RCOOH and CO3. They will give RCOONA plus H2 plus CO2. So this reaction is also used as a test for the carboxylic acid in the laboratory. The liberation of CO2 in the form of bubbles and treatment with NaHCO3 indicate a carboxylic functional group in the compound. Right. Now, let's see the next thing that is the reduction of the carboxylic acid. So basically the carboxylic acid are reduced to a primary alcohol by a litmus aluminum hydride that is LiLH4. Sorry, litmus it's being lithium aluminum hydride. So carboxylic acids are reduced to the primary alcohol by the reduction with the lithium aluminum hydride like this is phenyl ethanoic acid also known as no. Okay, benzoic acid. So when they are treated with the LiLH4 or S3O, they will convert into the 2-phenyl ethanol. So we can say that here the benzoic acid will convert it into alcoholic group. Now, what is HVZ? That is Hell, Vollard, and Jelensky. So reaction similar to aldehyde and ketone, carboxylic acid under halogenation at alpha carbon atom using Br2 or Cl2 in the presence of phosphorus or phosphorus trihalide. So what is HBZ reaction? This one is very, very, very important reaction. So just try to learn this reaction. Right. So reaction similar to aldehyde in ketones, carboxylic acid undergo halogenation at alpha carbon atom using Br2 or Cl2 in presence of phosphorus or phosphorus trihalide known as HBZ. For example, we have a butanoic acid like CH3, CH2, CH2COH and when they are treated with the Br2 and the red phosphorus in presence of water, they will convert it into 2-bromobutanoic acid, also known as the alpha bromobutanoic acid. So alpha halo acids so obtained are useful immediate in the synthesis of other organic compounds. So let's see the synthesis of acid derivative. Like we have a carboxylic acid. So we can derive from carboxylic acid, we can derive carboxylic acid halide, ester, we derive amide and carboxylic acid anhydride. So from the carboxylic acid, we derive the acid derivative like carboxylic acid halide, ester, amide, and carboxylic acid anhydride, right? So let's see the formation of acid chloride. Carboxylic acid basically react with the SOCl2, PCl3, and PCl5 to give the carboxylic acid chloride, also known as the acyl chloride. As we can show here, carboxylic acid when they are treated with the thionyl chloride, SOCl2. Right, this is nothing but SOCl2 only. This is SOCl2. So when they are treated with the SOCl2, they will form an acid chloride. Similarly, when this is treated with the PCl3, phosphorus trichloride, they will form 3RCOCl. Similarly, with the phosphorus pentachloride, they will form this, right? Now, so this is how we know this thing, that how we'll get this, right? So this is the way to get this all these things. So we already cover all the reaction related to this chapter as well, right? So this thing being very much clear that what type of concept that we need to understand in this chapter. So these are the basic concept that we need to understand here, right? Let's quickly summarize all these things that what we study today. Okay, so we study about the aldehyde and ketone, that what is aldehyde and what is ketone. And when the two alkyl group are present, they must be ketone, and the one alkyl and one hydrogen is sufficient, that one hydrogen must be present for a group to be aldehyde. Right, so this we already study about this thing. We also study about the vanillin, which is used for the vanilla flavor or camphor. Uh, there are some example. Yeah, this is the first method in which you will get the oxidation of primary and secondary alcohol. That is how will you prepare aldehyde and ketone. So by the oxidation of primary and the secondary alcohol, we'll get this. When the oxidation of the primary alcohol K1 4 K2 Cr2 then we'll get the aldehyde. So this aldehyde, the aldehyde will be further converted into CH3 COH, carboxylic acid. Right? This will also convert it into carboxylic acid. So for to stop this at this level, we need to add in a PCC, PDC, right? So PCC, that is the palladium chlorochromate or platinum dichromochromate. So these are the region that is used to stop the reaction at the aldehyde level only, right? So this is how what we need to do in the order to convert this thing. Now, hydration of alkynes as well. So hydration of alkyne can give an aldehyde or a ketone. So Marconic hydration need to give ketone, where the anti-Marconic hydration given a aldehyde. Similarly, Friedel-Crafts acylation, that is aromatic ketones, can be prepared by the Friedel-Crafts alkylation, or with the example of such reaction, we already discussed this thing. Structure and the physical properties. So in both the aldehyde and ketone, the carbonyl carbon and the oxygen atom are sp2 hybridized. So this is the important condition here. Therefore, the group attached to the carbon atom and oxygen are present in a plane. So we have sp2 hybridization of both the carbon and oxygen. Now you can see in the figure that pi bond is formed by the overlap of the p orbital of the carbon and oxygen atom in this way, right? In this figure. So the p orbital are present in the plane perpendicular to the plane of the molecule. Note that the presence of two lone pair of electron on oxygen atom, right? So we also know that oxygen is more electronegative than carbon. We know this thing. Hence, it attracts the electron of the carbon-oxygen double bond, resulting in the appreciable polarization, right? So the oxygen atom does acquire a partial negative charge, whereas the carbon atom get a partial positive charge. So this polar nature of the carbonyl group makes the oxygen atom more nucleophile and basic, while the carbon atom become less electrophile. Right. So I hope this is clear to you. Just for you. Right. So this is clear to you that what thing is taking place. So carbon atom get a partial positive charge, This polar nature of the carbonyl group make the oxygen atom nucleophile and basic, while the carbon atom become electrophile. The physical properties and the chemical reaction of aldehyde and ketone are direct consequence of polarization. Right now, as we also seen here, the reaction of aldehyde. So in the you'll find there are the three center of reactivity. So three center of reactivity means they are the prone to attack by the electrophile. They are susceptible to attack by the nucleophile, that is carbon, and they have also very acidic hydrogen. We also have right. This is also known as alpha carbon. So this is CH3 CHO. So CH3. This structure we can remember like this is CH3 and this we have some alkyl group like CH3 or V anything, and this is CHO. So this is alpha carbon, this is alpha hydrogen, right? So we have a three attacking group here. The one is that is prone to attack by the electrophile. This is susceptible to attack by the nucleophile, and this is alpha carbon. This is acidic hydrogen, right? So this is how we can remember this thing. So since the oxygen atom is nucleophilic in nature, so it is attacked by the electrophile. Whereas the carbonyl carbon is electrophile in nature and hence it is attacked by the nucleophile, right? So the third site of the reactivity is hydrogen atom present at the alpha carbon atom. So it is acidic in nature and give typical reaction which will be already studied in this class, right? So it is also important to know that this point I guess we already covered, right? Yeah. So they will undergo nucleophilic addition reaction, aldehyde and ketone. So the first reaction that will they undergo, that is nucleophilic addition reaction. Like in generally, the addition of the nucleophile on the carbonyl carbon can be represented as nucleophilic addition reaction. So what is the mechanism? So under the basic condition, the nucleophile attack to the carbonyl group will have tetrahedral intermediate. So subsequent to this, a protonation from the solvent H2O or alcohol takes place, right? This is shown in the below. Like here, we can observe that nucleophile attack to this carbon having positive charge. So the tetrahedral intermediate will be formed. Now, we have a water and we also have a H2O, right? So we have a water and we have H2O. This oxygen become negative charge after gaining electron from this double bond. So now this is the tetrahedral product. So what will happening here? This negative charge is, here removal of an H2O will be taken. So from where this H2O will be removed. So if this H2O will be removed, what we will get? We'll get nothing but OH negative, right? OH negative. So however, in the acidic addition, the first step is the protonation of the carbonyl oxygen takes place and the nucleophile then attack in the second step to the carbonyl carbon and the addition proceed as completed. So this is how we'll get. We already seen about the formation of cyanohydride. That is how cyanohydride will be formed. As basically carbonyl compound react with the hydrogen cyanide to give cyanohydride. Right? Similarly, a hemiacetal also forms when the aldehyde and ketone react with alcohol to give the hemiacetal. Right? So hemiacetal have an OH and OR group attached to it and the same carbon atom in their molecule. When an excess of alcohol is used, a second molecule of alcohol react to give an acetal. Acetal are stable in basic solution and therefore used as a protecting group of an aldehyde and ketone, where the acetal can be converted back to the carbonyl compound by the treating them with the dilute acid of the reversible nature of the above reaction, right? Now, formation of alcohol Grignard. So the formation of alcohol Grignard region. So this we already know that whenever the uh, Grignard region is treated with the formaldehyde, we'll get the primary alcohol. Similarly, when the Grignard region is treated with the aldehyde, we get the secondary alcohol. And when you treat the Grignard region with the ketone, we get the tertiary alcohol. So this is the sequence in which you'll get the different type of alcohol when you treat a carbon compound with the Grignard region. Right? So this is the elimination or a condensation reaction. So basically in the condensation reaction, ammonia and its derivative, that is aldehyde and ketone, they react with ammonia and the primary amine to give the imines. So this one is also very important role. So they will form imines here, right? Which are compound having carbon nitrogen double bond. So if someone asks what is imines, so imines is nothing but the carbon nitrogen double bond compound is known as amines. So it appears that during the above reaction, a molecule of water is lost from the primary amine and the carbonyl compound. So this reaction with the other derivative of ammonia are given below. that in the oxime, hydrazine to hydrazone, and phenyl hydrazine to phenyl hydrazone, 2,4-DNP, that is 2,4-di nitrophenyl hydrazine. So 2,4-di nitrophenyl hydrazone will get. So this will all get this too. The oxygenated reaction will also get the Wolff-Kishner reduction, right? So we'll get the Wolff-Kishner reduction as well. So this is how will you get this thing. When an aldehyde or ketone is heated in a basic solution of hydrogen in a high boiling alcohol, then the carbonyl group get converted to the methylene, that is CH2 group. Right. Now Clemenson's reduction, that is it is carried out in the acidic medium using a amalgam chain. So this you also remember, that is in this Clemenson's reduction, if you treat with the haptenone or any aldehyde with the zinc amalgam or HCl2O will convert this into heptane. Right. Last, we already saw a study about the oxidation of aldehyde. So basically, unlike ketone, aldehyde can be easily oxidized to carboxylic acid using a variety of oxidizing agent. Like this reagent can be chromic acid, chromium trioxide, permanganate, or silver oxide. So you have already did this. So silver ion selectively oxidize CHO group. This formed the basis of Tollens reagent. It involved the addition of mixture of aqueous silver nitrate and aqueous ammonia, which is also known as the Tollens reagent, right? So this is the now formula for the Tollens reagent, that is AgNH3 twice complex, right? So if an aldehyde is present, it get oxidized to the carboxylic acid, whereas Ag plus ion are reduced to form silver metal, which get deposited on the walls of the test tube, and this gives a mirror-like shining appearance, right? Right. So I hope this thing are clear. So we study all the important reaction in detail, right? We already cover all this chapter. So you just try to solve the questions related to this thing. In next class, we are going to start a new chapter, that is organic compound containing nitrogen, and last biomolecules and chemistry and math. So we're left with only three chapters, right? So try to do questions on this topic. Try to do as much PYQ as you can, so that you know what type of question generally they were asking in your exam, and what type of question maybe come in your exam, right? In your coming exam. So try to learn this thing. Try to do a practice of question as much as you can, so that you can able to solve the question, right? So let's meet in the next class. Till you just revise all this thing and learn this thing, right? So take care.